Okay, so let's recall what we proved in the previous analysis video. There we proved that if A and B are two real numbers and A is less than or equal to B and F is a monotonic real valued function with this closed interval as its domain. That is, this is monotonic. Then F is Riemann integrable over that interval. Now we are going to change this closed interval to any type of bounded interval. Now, this is automatically a bounded function. We already saw this when we proved this fact. Because F is monotonic, it is a bounded function, and actually for example, if it is monotonically increasing, then it takes on a maximum value at the point B and a minimum value at the point A. If it's decreasing, the opposite happens. So the function is bounded. However, if we change the type of the interval, then simply being monotonic is not a guarantee for boundedness. One example that we already considered when having a similar discussion about continuous functions, we can now also consider. Consider this function. And its rule is this. Okay. It is continuous, we know that, but now continuity is not what we are concerned about. It is monotonic, it's monotonically decreasing, its graph is like that. But in this interval, it's not bounded. That we have already seen before. So that's why if we now change the interval, we have to additionally assume that the function is also bounded, because otherwise we won't be able to talk about Riemann integrability. For example, you cannot even talk about whether this function is Riemann integrable or not, because it's not bounded, okay, in spite of being continuous. And now we do so in this corollary. In this corollary, we start off like how we started that one, but now let I be a bounded interval. That means the boundary points of I are real numbers, but I can be an open interval or any of the two types of half open intervals. I can be this also, but I can be of the other types as well. And F is a function from I into R, and let F be monotonic and bounded. Then F is Riemann integrable, just like this one. And the good thing about this is that the proof is essentially an already encountered proof, where you just have to modify two things. And I want you to do this. You write down the proof of proposition 1153 on paper, and then in places where you have the word continuous, you replace that with the word monotonic. And where we have used corollary 1152 in that proof, you just write proposition 1161, and then you read it. You will see that that becomes the proof of this. That's just it. With only these two replacements, you have the proof of this corollary. Okay, so after this, there is a proposition. So next, let's see that. Actually, the proof of this corollary is the first exercise. That is, it is exercise 11.6.1. Okay, so this is the solution to that exercise. Now next we are going to see proposition 11.6.4. It has the name also. Integral test. And it states this. Let f be a function on the set of all non-negative real numbers into the set of all real numbers be a monotonically decreasing non-negative function That means not only is this function monotonically decreasing, but it's non-negative also, in the sense that all its values are non-negative real numbers. So although we have taken the range as R, actually you can take this itself as the range, because all the outputs are non-negative real numbers. Then the series summation f of n, where n varies from 0 to infinity. Here n of course is an integer, I mean a natural number. The series is convergent. Convergent if and only if this is finite. Let me write it here. Supremum of integral of f over the interval 0, n as n varies over the set of all positive real numbers is finite. Finite means it's a real number. So let us see what it says once again. We have a monotonically decreasing non-negative function f of this type. The inputs are non-negative real numbers, and because of non-negativity of the function, the outputs are also non-negative real numbers, and it's monotonically decreasing. What does that mean? It means that if x and y are two real numbers there in that ray, in that interval, with x less than y, then it implies that f of x is greater than or equal to f of y. That's what being decreasing means. If we had in place of simple monotonic decreasing properties, strictly monotonically decreasing, then you would have strict inequality here. That's not the case. We are simply given that it's monotonically decreasing. Okay, so that's what f is. Then the f values at the natural numbers give us a series of real numbers. That series is convergent if and only if this quantity is a real number, is finite. What is this quantity? This quantity is actually the supremum of a set of integrals where the elements are integrals of f but over different intervals. Here capital N is not necessarily an integer, n is a positive real number. As you change n over the set of positive real numbers, the intervals change and the integrals change. So the supremum of that set of integrals being finite is equivalent to this series being convergent. That's what we have to prove now. Okay. So this is also one exercise. This is exercise 1163, the third exercise. The second one is something we will see it afterwards. So let's now see the proof. Let us note one thing in the beginning itself. Consider this integral, forget about supremum, everything. What is given to us about f? F is non-negative, fine, but other than that, f is monotonically decreasing. And if we restrict f, what is the original domain of f? The original domain of f is this. So for any n, any positive real number n, we can restrict the f on this interval. That restriction will also be monotonically decreasing naturally. And hence, by what we proved in the previous video, this integral will exist. Or in other words, f is Riemann integrable over any such interval. So in any case, with this supremum, we don't yet know whether it is finite, whether it's a real number or it's plus infinity or anything like that. We at least know that each integral exists. So this is what we are going to write first. We will also have to recall what that result was that we are going to refer here. Proposition 1161. By proposition 1161, this exists for all n greater than 0. And here existence means being a real number. Okay. Now what we do, we of course have to prove two things. If that series is convergent, then this is finite and then the converse. If this is finite, then the series is convergent. Let us first assume that the series is convergent. And let's give its sum also a name. Let's call capital L its sum. And this we are going to write at once. Let L be the sum of this series and it's a real number. So this is our hypothesis that the sum is a real number. So our hypothesis now is that the series is convergent. We have to now prove that this quantity is finite. Okay. So what can we do? In order to estimate this integral or these integrals, we have to consider some carefully chosen partition of this interval. So this is how we do it. Now, for any n greater than 0, let me repeat again, n is not a natural number. In other words, n is not an integer here. N may be a fraction or may even be an irrational number. It's simply a positive real number. I keep saying this because normally we use this type of things for integers. So for this, you have to consider the partition, or let me write like this, that way it will look better. Consider the following partition of the closed interval 0, n, and this is the partition. Closed open interval 0, 1, then closed open interval 1, 2, and in this way the subintervals in the partition go. Eventually, at some stage we reach this. You recall that this is the floor function value of n, the greatest integer less than or equal to the real number n. -1, keeping the pattern intact, this side is closed and that side is open. But then the final interval looks like this. Closed interval floor value of n, comma, closed interval n, because we have to ultimately include n in some subinterval. So this last subinterval is not like the others. Okay. Now what are we going to do with this partition? Let's see. Now what we will do is that we will straight away consider this integral for that n. Keep in mind that here n is, although for a given n we are doing all these things, but this n can change. Okay, so we consider this integral. Because we have already noted that this integral exists, its value is also equal to the upper integral value, also equal to the lower integral value, but that we won't use here. This integral is, because it exists, equal to its own upper integral value, upper integral of f. And that is why this thing is equal to the upper integral. But now let us recall that result where we link the upper integral with the upper Riemann sums. What does that result say? It says that the upper integral of a function is the infimum, the greatest lower bound of all the upper sums. And that result is proposition 11.3.12. Now, by proposition 11.3.12. So what did I just say? The upper integral is the GLB, greatest lower bound of all the upper sums. In particular, it's the lower bound. That means it will be less than or equal to every upper sum. And an upper sum comes from what? A partition. In particular, this quantity will be less than or equal to that upper sum of f which corresponds to this partition. So that's what we are now going to use. So we straight away write now by proposition 11.3.12, the upper integral is less than or equal to the upper Riemann sum of f corresponding to this partition, which by definition is this summation, because we are talking about upper sums. So this will be supremum of f of x x varies over j times the length of j, where j is a subinterval in P. All right. Now, can we guess what this suprema will be? Let's look at the intervals, okay, and see what the supremum will be. Do not forget that it's given that f is monotonically decreasing. That means on this interval, for example, if you think of the graph of f, it goes like this. So where will the supremum be attained? At the left end point, because after that it likely decreases. It may stay the same, but it likely decreases. So f of 0 is the supremum value of fx for j equal to 0, 1. All right, so the first term that corresponds to that j has f of 0. Okay, so this supremum part has been figured out. Times the length of this interval. Length is 1. That means we are going to have this. Okay, I don't have that part, but you understand 0, 1, 1, 2, like that it's going. So this will be equal to, this upper sum is equal to f of 0 times the length of that interval, which is 1. After that, here we had 1, 2. On this interval also, due to the decreasing nature of f, the maximum value is attained at 1. So you write plus f of 1 times the length of this interval, that is also 1. So like that it goes, and we reach this interval. Here also, the decreasing nature of f makes the maximum at this point. Okay, it assumes the maximum value at this point, f. Floor value of n minus 1 times the length of this interval. This interval also has length 1. Fine. Plus. But now also, on this interval also, the maximum is attained at the left end point. So we write this times, this time however the length is not necessarily 1. We have to actually write the length, and the length is this. Okay, so in trying to estimate this upper integral, we have got this upper bound for that integral. Okay. But now, note this. we already know a property means it comes directly from the definition of this greatest integer function. Recall that we have these inequalities. Plus 1. Because this is by definition the greatest integer less than or equal to n. It's the integer on the left side of n that is the closest to n. So the next integer obviously has to exceed this n, and that's why floor n plus 1 is greater than n. Now from this second inequality, what do you get? N minus floor n is less than 1. So although we do not get 1 here necessarily, actually this is less than 1. So we can now write less than, or if you want you can write less than here also, but I am simply writing less than or equal to because we just need that. F of floor n minus 1 plus f of floor n. So I have replaced this by 1, and that's why we have an inequality here. Oh, just now I said that if you want you can write strict inequality, but actually you cannot necessarily write that. You see, in fact, what have we done here? Because of this inequality, we have this entire thing, but how? You need to multiply both sides of this inequality by f of floor value of n to get this, no? Times n minus floor n, and that will be less than f of floor n. However, f is a non-negative function. That means any f value is either positive or 0. That possibility is there. If this f value is 0, we won't have strict inequality. We will actually have equality. That's why we have to write this. And note how the non-negative nature of f is essentially used here. We need that. Otherwise, we won't have these things. Now, if you write this as a series, as a finite sum, it looks like this. Floor n. Okay. So that means our upper integral, which actually is the integral, is less than or equal to this. Let us write this separately. So we now have the integral of f, which is also equal to the upper integral, less than or equal to this. But let us now go back to that series. Okay. Remember, we started our argument by assuming that that series is convergent. But so far we have not used that fact. Since f is non-negative and the series converges to the real number L. Proposition 638 implies that L is the supremum of these partial sums n equal to 0 to, let me write capital M, where M varies over the set of natural numbers. Now, what is this? This is a result that we proved when we were studying sequences of real numbers, monotonically increasing and decreasing sequences of real numbers. Okay, let me now clarify this. You have this infinite series. Now, this is not a part of the proof. This is our own, for our own understanding. We have this infinite series where, due to the non-negative nature of f, all the terms of this series are non-negative real numbers. Now, if you think of the partial sums of this series, what will the terms of that sequence be? The first term of the sequence of partial sums will be this. The second term will be this. The third term will be this. Because the individual terms are non-negative real numbers, so this becomes an increasing sequence of real numbers, right? I mean, each new term you introduce may either be 0 or a positive real number. So the next term either is the same or it's more, okay, in this sequence. And for such a sequence of real numbers, you know precisely when it is convergent, namely when it is bounded from above. A monotonically increasing sequence of real numbers converges if and only if it has an upper bound. And when it does have an upper bound, what is the limit? The limit is the supremum of the sequence, the least upper bound. Now, this is such a sequence, and it's given that it converges to L. So, L has to be the supremum of the partial sums. And the partial sums are this finite series where n varies from 0 to m, where m itself varies over the set of natural numbers. For example, if capital M is 0, you get this. If capital M is 1, you get this term, like that. And the result that tells us that every monotonically increasing sequence of real numbers converges if and only if it's bounded above, and when it's bounded above, it converges to the supremum of the sequence is this proposition 638. All right. So, now what? Now we know that L is the supremum of these partial sums, and this is one such partial sum. Okay, another question may arise in your mind. How do we know that this floor value is a natural number? You think of n. What was n? N was a positive integer, right? Let me write that same inequality like this. From this inequality, what can you say about the floor value of n? The floor will be an integer. That much we already know because it gives integer values. It's an integer valued function. What is floor of n? Floor of n is the largest integer less than or equal to n. 0 is already an integer less than or equal to, less than n means less than or equal to n as well. And this is the largest. So obviously, we will have this, and it's also an integer. So that is why it's a natural number. And that means this is one such partial sum whose supremum, the supremum of all such partial sums is L. So this is less than or equal to L. Right? So that's how we are getting the fact that regardless of what our real number n is, whatever positive real number n we can think of, this integral is bounded from above by L. So the set of such integrals has an upper bound, which itself is a real number. And that's why, by the least upper bound property, the supremum of that set exists, which means that it's also a real number. Hence, and keep in mind that we have been doing all these things for any positive real number n. So that's why L doesn't depend on n. L doesn't depend on n. L is that sum of this series. It's independent of n. It's already there from the beginning itself. Hence, this exists. Okay, so that is one half of the proof. Now we go for the converse. Conversely, let the converse, of course, starts by assuming that this is real. And now then we will prove that the series is convergent. Excuse me. And this time also, in this converse part also, we will have to carefully choose a partition. Let us give this quantity some name, say capital M. We call that one capital L, so let's call this capital M. Let M, which is the supremum of this, be finite, means let it be a real number. Okay. So now, this time, however, what is our aim? Our aim is to now prove that this series is convergent, which means that we will have to show that the sequence of partial sums is convergent. The fact that f is decreasing and, well, not exactly that, but the fact that f is non-negative still is there with us, and whatever we discussed here about the series still stands, which means that the sequence of partial sums is an increasing sequence of real numbers. And just now I said moments ago that such a sequence converges if and only if it is bounded from above. It has a real number upper bound, proposition 638. So if we can show that the sequence of partial sums of this series has a real number upper bound, then we are done. It will be convergent, because whenever the sequence of partial sums converges, then only by definition the series converges. So that means we have to concentrate on partial sums. A partial sum is going to look like this: summation f of n is equal to 0 to n. But now this n is a natural number. Okay, we will consider n to be a positive integer actually. For any integer, now n is not a general positive real number, but it's a positive natural number, positive integer. Consider the following partition of 0, n. Let's give this partition the name Q. It's somewhat like P, but actually different also. What we will do here instead is we will, in the beginning itself, isolate the left endpoint 0. Okay. In P we considered closed open intervals. Here we will consider open closed intervals. Open 1, closed 2, like that if one goes, then one eventually has, we don't need floor here because we have integer. I was going to write floor, but that's not needed. n minus 2, closed n minus 1, open n minus 1, closed n. Because we adjusted this in the beginning itself, so we got to keep the pattern and reach the end, okay, with n accounted for automatically. Now, what can we do with this partition? Let's see. This time around, we will use lower integral instead of upper integral. I mean, the fact still stands, and it's still there, that for any such n, this integral exists, right? That we noted in the beginning itself, and so is equal to this lower integral. All right. So let's use this fact. Now, integral of f, well, if we start like this, no, this is something that we will use. Okay, so we won't start with this. In fact, we should start with that partial sum, yes. Okay, that's how we should start. And slowly we should move towards the integral. Let's consider this partial sum, n equal to 0 to n. What we do is this: f of 0 plus, so for some reason we isolate the 0 term, the term corresponding to n equal to 0, we write it separately and write the rest as the sum. All right. Now we want to make this the lower Riemann sum of f corresponding to the partition Q. In fact, we claim that this is the lower Riemann sum of f corresponding to Q. Straight away, let's just write that and see if it really is. Summation infimum, we use infimum in lower sum, infimum of f of x, where x varies over j times the length of j, and j itself varies over q. Shall we really get this? Let's see. Of course, thinking from this one and getting this one is tough. So instead, let's just think of this one. Again, we have all the intervals here in front of us. So we know what all the j's are. So let's just see what happens for each j. The first j is this degenerate interval. Because that gives us the singleton set f of 0, so the infimum is simply f of 0. We already have an f of 0 here, but forget about that, okay. We have f of 0 here times the length of this degenerate interval, which is also 0. That is 0. F of 0 times 0 is 0. So that term vanishes. The term in this sum corresponding to j equal to this degenerate interval, because it is degenerate, it vanishes. But what about the others? Consider this one, 0, 1. The fact that f is decreasing is still there with us. So on the interval 0, 1, also the graph of f kind of comes down from left as we move from left to right. So where do we attain the infimum? At the right endpoint, because the graph is like this. There, in case of upper sum, the supremum was attained at the left endpoint. Now the infimum will be attained at the right endpoints. So for this j, that infimum is f of 1 times the length of this interval, which is 1. So we get f of 1 here, the first term of this series. Similarly, if you are on this interval, then the infimum is attained at 2, f of 2 times the length of this interval, which is 1. So f of 2. So that way you get the second term. If you continue like this, you will get f of n minus 1, and finally you will also get f of n times the length of this interval. All these intervals except the first one have length 1. That is why this indeed is equal to this series. But when you write out all the terms, you do lose one term, which is f of 0 times 0. And that is why we isolated f of 0 in the beginning itself, so that we get this series. Okay. Alright, now let's think of the lower Riemann integral of f. The lower Riemann integral of f over that interval, again by that proposition, whatever it was, 11, 3, 12. How is it linked to the lower Riemann sums? This is the least upper bound, LUB, of the set of all lower Riemann integrals. Lower Riemann sums of f as you change the partition. This time it's the least upper bound, it's an upper bound. So it will be greater than or equal to all such lower Riemann sums. In particular, it will be greater than or equal to this lower Riemann sum, and that's why you can replace the lower Riemann sum by the lower Riemann integral. This type of inequality will be obtained. Plus all right. Oh, and now, okay. You see, this thing will be equal to what? Will be equal to the ordinary Riemann integral of f over this interval. However, what is capital M? Capital M is the supremum of all such integrals, and it's a real number. So the supremum will itself be greater than or equal to this naturally. Let me keep that one. Let's not erase that part. So that is why if I naturally continue, first of all, this will be equal to f of 0 plus this. Now because m is the least upper bound of these things, so this is less than or equal to f of 0 plus m. What have we proved? We have proved that all the partial sums of that series have this fixed number as an upper bound. And that is why the sequence of partial sums which already is monotonically increasing will be convergent, and that's why the series will be convergent. In fact, if you want to use a ready-made result which says specifically this, you do not have to go back to the sequence chapter. In the series chapter, the 7th chapter itself, you have a proposition 731 which tells you that in such a case where all the terms of the series are non-negative, such a series is convergent if and only if the upper sums are bounded from above by a real number. So let's just use that. So by proposition 731, if you remember the third section of the chapter on series is on a series of non-negative real numbers. There the first result is this. This is convergent. So if you know how to choose partitions, you can do anything with integrals. You can play with partitions and see which one fits the best for your purpose. The partitions that are used here may not be the best, I don't know. Okay, I just came up with them and they worked, so I just kept them. You may find some other partition which will maybe give you the result much more quickly. It's possible. Okay, and if such anything like that you find, I would like to know. So you can write in the comment section if you find any such thing. But this is the proof of the integral test. After this also we have one more corollary, I think, in this section, but we will talk about that in the next analysis video. So let me just end the video here itself. The next upload is this coming Friday. As usual, we have calculus. So see you on Friday. Until then, this is me, Lucifer, from A Mathematical Room. Have a nice night.